Hi, it's time for another math easy solution. Time to discuss further into differential equations and now look at the very interesting topic of continuously compounded interest. And to help illustrate this concept, I'm going to work through this starting example here, which says if $1,000 is invested at 6% interest, compounded annually, then basically what this means, again, this compounded annually, this means that we apply the 6% to this initial value of 1,000, and then we add it upon our initial value of 1,000. That's the whole idea of compounding annually, or this one's doing it once per year. So for this specific sum, after 1 year the investment is worth, well, again, what the whole idea of compounded interest is, so you start with 1,000 here, then we add to this 1,000 6% of that 1,000. So this is going to be 6%. So times this by 6%. In other words, you could factor out the 1,000, so we get 1,000 out. So I'm just going in extreme detail. So now we have a 1 plus 6%, and again, 6% by definition, percentage is just a ratio of 100. So this is the same thing as writing 1 plus 6 over 100. That's just what 6% means. And then this 6 over 100, that's just 0.006. And 0.06. So this is the same thing as writing 1,000, 1 plus 0.06. And now add that up, we get finally 1,000. And then we have a 1.06. Like that. And now if you were to calculate it, you get, well, 1,000 times 1.06, that's just 1060, which makes sense because 6% of 1,000, that's just 60, because 6% of 100 is 6, times by another 10, so 60 plus 1,000, so that's just 1060. So after 1 year adding interest to it of 6%, because we're compounding it annually, in other words, once per year, we get 1060. That's the worth of our investment right now. So now after 2 years, if we want to find what the investment is worth, well, we're going to do the same thing but with this new starting value. So now we're going to compound interest onto that new value. So 1060, again, we're going to do 1060 times it by, so 1060 plus 1060 times by 6%. And we're going to get through the exact same stuff. This is going to be, well, 1060, and then 6%, we're factoring it out, 1 plus 6%. Etc. So this is going to be, well, the same thing as before. So this is going to be 1060, and then this is 1.06. So notice we got to this point right here, but this 1060, that just equals to 1,000 times 1.06. So this equals to 1,000 times it by 1.06 times it by 1.06. In other words, this is going to be 1,000 times it by 1.06 to the power of 2. And now if you were to calculate this out, like here, we get, well, 1,000 times 1.06 to the power of 2. That's just 1123 and 60 cents. So this equals to 1123 and 60 cents. Yeah, so I'll just circle this, and I'll circle this as well to show that's the answer for the previous one. So yes, so as you can see, the pattern that's arising, all we're going to do is, so basically if we were looking at after T years investment is worth, well, that's just any number of years. As you can see, the pattern for the first one, after 1 year, we have this 1,000 times 1.06. You could also write to the power of 1. Then here we have this 1,000 after 2 years to the power of 2. So after T years, the worth should be, or the worth is, so basically what we could write this is going to be now, well, 1,000, so after T years, this is just going to be times this by 1.06, because we have a 6% interest rate, to the power of T. So that's for any number of years. If it's 4, you put a 4, if it's 3, you put a 3. Let's erase this. Let's put the 2 like that, better. But now if we want to go even more general, because right now we started with the example of $1,000, but let's say if, in general, if an amount AO was invested as opposed to 1,000, so this is just any number AO or A0 here, is invested at an interest rate R. So now instead of 1.06, instead of this 0.06, which is, well, remember this is just 6%. So instead of that, if we had just any generic one, then after T years it's worth, well, A0 times it by, this was 1.06, but we're adding, again, recall, this is just 1 plus this R. So we're going to write 1 plus the interest rate R and then the power of T. So that's the same thing as 1.06, like that. So this is what our generic amount is. And in this case, this is compounded annually, if we're doing by years. And now moving forward, basically another point about interest rates is that usually, however, interest is compounded more frequently than just simple annually. So in other words, let's say it was compounded n times a year, for example, biannually, quarterly, etc., or even daily. So then in each compounding year, the interest would be, so if you were given an annual interest, we need to make it for that specific number of times in the year. If it was biannually, you would divide that interest by 2. But so if it's n times a year, you would divide this annual interest by n times. And then what we also get is, well, we get n times t compounding periods in t years. So the value investment is, well, before I get to that value, what I mean by this is, let's say for example, for the example, let's say you have an annual interest rate. Let's go annual. This equals to, let's say it's 12%. It's easy to divide, and then we want to get, well, but we want to compound instead, let's say monthly. So what we would do is get a monthly interest, and you could just divide this out by 12 months. Divided by 12, and this is our n equals to 12. This is n equals to 12 months. So that's what we have right there. This just becomes 1%, and then the total number of compounding periods in T years. Well, if we're doing, let's say after 2 years, we want worth after 2 years. Well, after 2 years, but we're doing it monthly compounding, so that means we're going to do 12 months per year. That's then times it by, well, 2 years to get 24. So that's how many total compounding periods. In other words, we have this n and this is t, so that's where we get this n multiplied by t from. So we put this all together, and now we're going to be looking at compounding the interest n times per year. The total worth is going to be after t years is going to be AO again, or A0 times it by 1 plus the new RN, or in other words, this is the same thing as RN if it was biweekly, etc. And then that RN is just R divided by N. So a new interest rate is R divided by N to the power of N times T. Yeah, so that's, I'll just keep that arrow there. So this is what our worth would be if we were compounding it more than one time per year. Yeah, and to help illustrate this concept, basically let's look at the example. Well, for instance, after 3 years, so our T is 3 at 6% interest, a $1,000 investment will be worth, well, if we're doing compounded annually, then this worth will be, well, basically that's going to be, our AOs is 1,000, so this is our AO, this is our R, and this is basically T. So T is equal to 3, R is 6, or 6%, AO is 1,000, and compounded annually means, well, we're compounding it once per year, because number N is N times a year, so this means, well, N is 1. So in other words, we're going to have 1,000, which is our AO, 1 plus, and then R, which is 0.06 divided by N, which is 1, so it doesn't change anything. And then this one we're going to have N, which is 1, and times it by 3. So the ones don't do anything. Yeah, so if we put this in a calculator, so 1000 times 1.06 to the power of 3, that's just 1191.016. And that's the same thing we were dealing with before. Again, that's this this one here doesn't change anything, so 1 plus 0.06 is just 1.06. So this equals 2. Let's go back to that number, 1191, and then round it up to 0.02, or roughly equal to. Put the $sign, 11, and then this is a 91, and round up to 0.02 like that. Yeah, so now if we were to compound it semi-annually, in other words, twice per year, so our n is equal to 2. So that's how many times per year we're going to compound it. So now what our worth is going to be is, well, 1000 times it by 1 plus 0.06 divided by 2, which is our n. This is 2 times 3 now. In other words, we get a, let's put the, so it doesn't look like it's 2.3. So 2 times 3, or in other words, we get 6 there. So this is roughly equal to, if you put in the calculator, 1000 plus 0.06 divided by 2 times by 2 to the power, to the power of 2 times 3. So this is 1194.05. So you get 1194, yeah, 0.05. So as you can see, this is more than our, it's about $3 more than our 1191.02 if we compounded annually once. Yeah, it's compounded annually per year as opposed to semi-annual. Yeah, so now moving forward, let's look at compounded quarterly. In other words, every 4 months, so n is equal to, well, 4 months. So that's quarterly. There's 4 quarters in a year. So we're basically compounding it 4 times. So our value of the investment now is 1000 times, well, 1 plus, this is going to be 1 plus 0.06, our interest rate for annual interest rate, divided by n, which is 4, to the power of, now we have a 4 times it by t, which is 3 years. So this equals to roughly, again, plug this into the calculator, we have here 1000 times 1 plus 0.06 divided by 4 to the power of 4 times 3. We get this, I'll round up to 1195.62 cents. So 1195.62. So as you can see, this is about $1.50 more than the compounded semi-annually, so it's not much difference now. And now moving forward again, let's look at monthly. So there's 12 months in a year, so we're compounding it, n equals to 12 times per year. So now what we get is 1000 times it by 1 plus 0.06 over, this is over 12, and now we have this 12 times 3 years. In other words, that's 36 there. And then this equals to roughly, go up here, put this in the calculator. So the only thing we're changing is this n is 12 now, and then 3, and now we have 12 times 3 years like that. Now our answer is this right here, 1196.68, and then ignore the other parts there. So this is roughly 1196.68. I think that's what it was. Yeah, 1196.68. And now finally, let's look at what happens when we compound it daily, and recall again the number of days in a year. That's, well, 365. So if we're compounding it every single day, or adding interest to the new sum every single day, that's just what compounding means. So we have 1 plus 0.06 divided by 365 is our new n. Now we have 365 times it by 3, like that. Plug this into the calculator, we get roughly equal to, right here, we just replace by 365, we get 1197.1996. We'll just round it up to 20 cents. So we get 1197.20 like that. So this is just under $1 more than the monthly compounded. Yeah, now from these simple examples, you can see that the interest paid increases as the number of compounding periods increases. So yeah, you're paying more because of the interest when you're compounding more frequently, but it's not that much more when you get to when you get more than n equals 2 or whatnot. So 94, so we had 91, 94, 95, 96, 97, so it's separated by a few dollars, but nonetheless they're still increasing. So now if we let n approach infinity, then we will be compounding the interest continuously, and hence the video title, Continuously Compounded Interest. So if we're literally compounding interest every possible time that it's available to do that, and that's with this concept of infinity, then the value of the investment will be, well, that will be that actual investment. If we're doing it, we'll call A of t the value of the investment after t years, and this equals to the limit, because we're compounding it however many times a year. We're going to assume we're going to compound it infinite amount of times in a year. So this is just equal to our A0, and now we have 1 plus the Rn. So we're just a limit as n goes to infinity, and then this is n to the power of t. So just make sure that was the right formula. So yeah, so we have here 1 plus r over n to the power of t. And now what my calculus book does is rearrange this in such a way that we can get the limit and the r and n's all by themselves to get rid of this t and ao. To do that, what it does here is multiplies this by r over r, so it's not changing anything. And then what it does is takes so what this means is now limit as n approaches infinity. This is just a0, and now we have this 1 plus r over n, r over n like that. And then what it does is actually puts this it separates this, and then takes power here. So we have this r divided by r. One of the r's will move it over here, and then I'll leave the other r right here, so that we have this n over r, and then separate this t times r. So we have n over r here, and then using just the basic properties of power functions when you have a power like that. So that's n over r like that. I'll just erase this and write in bracket tr. So we have that, and then this becomes right here, n over r is inside, and we can just take this on the outside. So I'll write rt, move the r in front. Yeah, so that's what we have, and I'll just put this back to normal, so nt, just in case if you download this notes and wonder why I did that. So we just have this r over r so that we could rearrange to get this right there. And the reason we do this is because now, and this will all make sense as I get further into proof of this. Basically what we have now, there's no n inside here, so this limit as n approaches infinity, again using the limit properties, and you can see all these in the video links below on the power functions properties and also the limit properties, because the only things that are that have the n value that we're taking the limit of is this inside bracket. Everything outside, there's no n on the a0 or ao. So what that means is we could write this as limit as n, actually no, limits are inside, that's what I meant. So this goes to a0, write this neater, a0 times it by, and then this is in the bracket actually, limit as n approaches infinity, because the only thing that's affected by this n going to infinity is the parts that have the n value. So now we have this 1 plus r over n, this is n over r, and this is all to the power of rt. So this is outside of the limit because there's no n value in this power right here, only the inside matters. And now what my calculus book does is simplifies this even further, and I'll get to this why. So what it does is looks at this part here and basically let's say let m equals to n over r. Yeah, so this is, if we let m equals n over r, just to simplify this, then basically as n approaches infinity here, because we're going to replace that, m also goes to infinity. So because here we just have n divided by r, as it's getting really, really large, regardless what the interest rate is, well, you're just m is also going to infinity. So what that means is we could rewrite this, this limit using the m term. So we get finally, draw a better line. So what we get is a of t is equal to a0, and then put this all in bracket, limit as m approaches infinity of, let's draw this infinity a bit neater, one more time. So then now we have here 1 plus r over n, that's, well, the flip side of this, that's n over r, that's just 1 over m. So 1 over m, and then this, what we have right here, n over r is just m. And then this is all to the power of rt, like that, right? This is a bit neater. Yeah, now the reason that I put it in this form, using this m, well, just because of this form, 1 plus 1 over m to the power of m, is because, as I just wrote down right here, the limit in this expression is equal to the number e. Yeah, this is actually equal to e, which is quite remarkable. I'll put that exclamation point out just so it doesn't look like it's a factorial. And I've gone over this video actually before, and I'll put that link in the description below. So basically, recall from my earlier video the number e as a limit. This e to the x is equal to limit as m approaches infinity, and in that video I used n, but here we'll just use m, just different variable, doesn't make any difference. So 1 plus x over m to the power of m, like that. So that's what the e to the x as a function, written as a function, is equal to when written as a limit. And if we were to look at e to the power of 1, or that's just e, that just equals to, well, limit as m approaches infinity, and now you plug in 1 for the x, we get 1 plus 1 over m power of m, which is exactly our value right here. So 1 plus 1 divided by m to the power of m, which is quite remarkable. In fact, it's so remarkable, I'll just write a wow like that, because that's just pretty amazing stuff when you can go finding compound interest, just doing it the practical way, finding a formula, taking a limit, and all of a sudden you get back to the number e, which as when I get further into this in this video, you'll see it's even more shockingly amazing. So basically, with continuous compounding of interest at interest rate r, the amount after t years, what we finally get is a of t, and I'll explain further what I mean by what's so shockingly interesting. So a of 0, this becomes e now, e to the rt. So this is what we have. Yeah, so what's amazing about this is, now that we have this formula, notice how it's the exact same form as what we've gone over in our differential videos in these past few weeks, actually. So if we were to differentiate this equation, in other words, take the derivative, so the derivative of this, that's just going to be dA over dt. So derivative in terms of time, this equals to, we have this a0. So the derivative of ERT is itself. Remember that this is constant. So the derivative of e to the power of whatever is itself, but then you have to multiply by the applying chain rule. So the inside the r constant goes down. So we have this RA 0 e to the RT. And again, this is just, well, our function again. That's just our A of t. So in other words, what we get, well, this is just R A of t. In other words, what we end up getting now is our dA over dt is equal to RA, or RA of t, which is very, yeah, this is the exact same thing as our other ones, which was dy over dt equals to ky. In other words, I'll just put it in bubbles in a cloud right here. Recall the law of natural growth or decay that I've went over in my earlier videos, and I'll put all that in the video links below in our exponential growth and decay video, natural growth. So just recall my earlier videos, we always had the dy over dt equals to ky. In other words, the growth rate is proportional to the amount of the size of that population, or whatever, in this case interest. Total amount that we invested. So the amount that the interest rate grows, or that the amount that investment grows, is proportional to the size of that investment at that time. Yeah, and as I just explained, this equation says that with continuous compounding of interest, the rate of increase of an investment is proportional to its size. So this is all the very fascinating and that shocking, amazing thing I was trying to point out, is all this work we got to in writing and modeling this compounded growth, and then looking at it when we take the limit to infinity. It pretty much it's like going all the way backwards and then finding out that it's the exact same thing as that law of natural growth that we went over many times in my earlier videos, and finally getting this equation, the fact that it equals E without having to take any natural logarithms or any assumptions as to that the rate increases by growth. So which is quite amazing. Or I mean the growth rate is proportional to the size, that's what I meant. So that's quite amazing. So now let's return to that example of 1,000 invested for 3 years at 6% interest. We see that with continuous compounding of interest, the value of the investment will be, well, that's just A at 3 years equals 2 now. Our A0 is, again, so A0 ERT, our A0 is 1,000, times it by E to the R, the interest rate, and our interest rate right here is 0.06, and then times it by, well, 3. So after 3 years, put another bracket here. So 0.06 times 3, and here if you calculate it out, here 1,000 times e to the power of 0.06 times 3, we get 117.217, we'll round it up to 22. So this equals 117, actually 1197, so 1197.22, which is very similar to our compounded daily right here, so which is 1197.20. But notice the equation here, which was for the daily amount, so 365 times per year. As you can see, this compounded formula is much more much more complex than our simple e to the RT formula, which is just like this, and we got pretty much almost the exact same answer, but only 2 cents difference. And I've written that here as well. So notice how close this is to the amount we calculated for daily compounding, which was 1197.20, but the amount is easier to compute if we just use continuous compounding, just using this wonderful E number. Anyways, that's all for today. Hopefully you learned from this very extensive example and proof video of compounded interest, and looking at continuously compounded interest, and showing you how that it all wraps around nicely with the number E and the law of natural growth that I've went over many times in our differential equations videos, and it's quite fascinating how we got to that point without assuming that it's that the growth rate is proportional to the size, just working around how it is, taking the limit and seeing that it's all matches perfectly, which is quite remarkable, and that's some of the beauty of mathematics. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.